Hi, welcome everyone. I'm Victor. How are you enjoying hybrid CppCon so far? It's an interesting experience. I know us Europeans are a little envious of people who can be there on site in Aurora, but we still can enjoy the great content and have all the live discussions in GatherTown or on Discord. So I'm happy to be a part of CppCon yet again, and hoping that next year I'll be there again on site with all you fine folks. So for today's session, we're gonna talk all about exceptional C++. And when I speak about exceptional C++, I don't mean that we're gonna cover golden rules or code smells or goals for better code. I'm very deliberate in talking about things that happen on the unhappy path. So you probably know me from other presentations I've done at conferences or from tools that I've helped build over the years, some of them longer than I care to admit, like Advanced Installer, and some newer ones that have become a staple on Visual Studio land, like Clang Power Tools to leverage LLVM compiler infrastructure from Visual Studio projects from right within the Visual Studio IDE. You can always reach out to me on Twitter. And of course, during today's session, feel free to post your questions in the Q&A tab in Zoom. I'll try to keep an eye open for this tab. And if I can address questions at a natural stopping point during the presentation or right in context, I'll try to do so. If not, I'll defer questions till the end. And if somehow we run out of time, I do invite you to join me in GatherTown after the session to do post-session discussion live there if you're so interested. Or you can always find me on Discord in the CppCon Discord and ask me any question regarding the topics I covered today. So let's try to dive into the topic. When we usually write code, we usually channel all our attention on the happy paths, on the interesting stuff happens on the business logic side of things. Yes, we do error checking and we try to handle eventful situations or critical errors or even logical errors, but we generally focus all our attention on the task at hand. But there are plenty of exciting things happening on the error handling flow too. And this will be the focus for today's session. So although not universally loved, exceptions are a very powerful mechanism to maneuver execution on the unhappy path. Yes, there are several alternatives out there, but I'm not going to do a pros and cons kind of session today. But we're going to discuss exceptions and all kinds of exceptions and maybe focus on the exceptional ones, if I may permit myself a pun there. Because exceptions are really everywhere. And I'm not talking about exceptions versus error codes or expected type of facilities to handle unusual scenarios or to pattern match or branch within the application code. I'm not even going to talk about exception safe code, although highly important in my opinion, or other error handling best practices. There are plenty of good talks about these topics, some from past conferences, and even some talks that I'm eager to see at this year's CppCon. I've seen some interesting related topics in the schedule, so I do encourage you to attend those. And we're not going to talk about some magical constructs that are going to make our applications run fast and secure and be robust. This talk is not about that too. So what is it about? Well, it's about the inner workings of the exception handling mechanisms and the beauty therein, and what we can learn from how these mechanisms are implemented, and all the intricacies of the mechanisms inside. And it's not going to be pretty like this. It's going to look more like this, to be honest. And yes, it's messy, but it comes with legacy considerations, and it comes with restrictions and performance considerations. And some bits are better left untouched, unknown. But some of the details are fascinating, and I think we can learn a lot from understanding how they work, and even leverage them to our advantage to build something more, to extract more from this context, and maneuver the execution the way we want it when such events occur. So this talk is more about decomposing the machine, the engine that drives these kinds of mechanisms, exception handling workflows, right from the CPU to the operating system and to the runtime and to the application code. So the whole pipeline of what happens when something exceptional occurs. And fairly so, I would say this talk is about exception internals. So just a disclaimer, I'm going to focus here because I have to choose something. I cannot possibly cover the whole landscape. I'm going to focus here on exception internals on Windows, both instruction set architectures, 64-bit and 32-bit. And I'm going to point to differences because there are several differences. I'm not even going to try to cover ARM on Windows because it's, for now, it's not as used as it will be in the future. And there are some differences that I don't have the time to cover today. And if you're interested in other systems, or even maybe exception handling workflows in freestanding environments or embedded systems, because yes, some people can do that too and simulate some exception flows there. There are some interesting other presentations that I encourage you to follow. So our focus today is on exception handling mechanisms in Windows. So life happens and you're going to be faced somewhere along the development pipeline with some crash in a form of other. I have here a stack trace with symbols, and we see right off the bat that it's an access violation at a particular address, and we see even a stack trace with the information about the crash. So this is what we kind of get used to seeing and debugging. So we have to address the elephant in the room, which is structured exceptions. You can play along and ignore the fact that structured exceptions actually exist on Windows, and maybe even wave your hands in the air that this is not standard C++. But if you program on Windows long enough, and if you deal with sophisticated components, or you do complicated systems configurations or integrations, somewhere along the lines you're gonna be faced with dealing with structured exceptions on Windows, and you have to understand how they work and how you can interact and hook into this mechanism. So just a quick primer for people that are not familiar with structured exceptions. They basically predate the C++ exception specification, and they're a very low level and in some situations efficient implementation of exception handling mechanism, and they're not even part of the C++ their language extension. Basically, you can leverage them in other contexts, even in C-like code. So to enable structured exception in a project, you have to use the async exception specifier, EHA. I've put links to documentation here. I'm not going to dwell too much on it. You can even enable it from the project settings GUI or at the MS build configuration file level. So basically, when, let's say, we have here a null pointer, a write exception, what's going to happen is the processor will not melt. Or maybe if we have like arithmetic exceptions, like let's say divide by 0, something like that. Any kind of hardware fault exception that might happen, the processor will not melt. What actually will happen is that an interrupt handler will be called and the operating system will take over, and this special mechanism within the operating system that handles structured exceptions will fire up and will start looking for ways to handle the event that occurred. And of course, we'll have an opportunity to hook into this mechanism, because if we don't, the standard implementation from the Steam runtime on Windows will basically just take down the program. But we can hook into this mechanism and react to what happened, log the event, inspect the event, take a snapshot of the event, some kinds of such events or exceptions are even recoverable. We can have a set of chain filters that we can set up to process or to find an appropriate handler for particular kinds of events, and choose to implement whatever reaction or behavior we desire for each particular event where we might be interested in. So the essence here would be to take a snapshot of what happened, and the application, the process that encounters such an event. To be more precise, the thread that encounters such an event basically is temporarily halted, and we can take a snapshot and see what happens, and we can decide what happens next, where the next instruction pointer will land, what will happen next. We're going to talk about exception unwinding and what happens to state objects, and we're going to drill down into how exactly this process goes from capturing the process state up to installing and looking up special handlers within the SEH mechanism to deal with exceptions. And it all starts with the context. And by context, the operating systems actually means processor state and a little bit about the memory. We'll talk about that later. This is a pretty big structure, but I'm gonna zoom in just a section of it so you can get a feel for what's in there. It's basically register information. So when we talk about context, we actually mean CPU context in this situation. And we're going to talk about the exception record. So the operating system defines an exception record, and it has an exception code. So all kinds of exceptions have corresponding unique identifiers, exception flags, which have special meaning depending on the type of exception in flight, a chaining pointer to chain such structures in lists. And here there are differences already between 32-bit and 64-bit implementations. For 32-bit implementations, we have a chained list of exception records. For 64-bit, we have a table lookup mechanism to be more efficient on the unhappy path. And the exception address and number of parameters and some lightweight exception payload there that has special meaning, again, depending on the exception code of the exception in flight. So we have here the slight difference, highlighted here, the slight difference between 64-bit and 32-bit implementations. The difference being the way this record is traversed when an exception handler is searched. So a simple linked list versus a lookup table. The pointer there, the field there in the structure is opaque, but it hides the fact that it's a chained structure. So if we go back to see a very simple example here, let's say we have an access violation, and that would be the code there for the access violation. And we have no next exception record in the chain. So this might be the last one in the lookup chain. We're going to focus on the 32-bit case just for now, because it's simpler. And we have the exception address, where the instruction address, the program counter was when the exception was encountered. And we have in the number of arguments, because we have two, we have the fact that it's a write fault. It could either be for an AV, it could either be a read or write fault, or a data execution prevention fault. And the virtual address of the data that was inaccessible. So the memory location that we try to address and faulted. So we have, and it all starts there. We have what it's called on Win32. Ignore the fact that it's Win32. Win32 is a legacy name that just means a Windows user level persona for programming Windows on user land. And it also applies to 32-bit. It's just an umbrella name that's stuck. So Win32 thread information block, TIB for short, it's a structure that stores information for the currently running thread, and it stores all kinds of information. And the relevant bits that are important for us are the FS segment register on 32-bit Windows. So we have explicitly FS 18H, and the GS register on 64-bit 30H. And the way we get this TIB, we can either use an NT function, NT current tab, that gives us this structure, NT TIB, or we can read directly from the FS segment register or from the GS register using these primitives to read the exact data there and basically cast it to the TIB structure there. So either way works. And the TIB contains thread specific exception handling chain. So each thread has its own exception handling chain. And yes, it generally stays contained within a thread, but you can do tricks to get an in-flight exception from a particular thread and basically rethrowing it into another thread to be handled there. There are specific scenarios where this might be useful, and I'm probably not gonna cover them during this session, but I'm happy to discuss about such scenarios maybe in Gather Town or afterwards. So, and of course, aside from the exception handling chain, the TIB also contains thread local storage information. So current structured exception handling frame, so SEH frame, and just to mention, on 32-bit Windows, stack unwinding is done in kernel mode instead, again, for efficiency reasons. So that lookup that is done and the unwinding process per se is done with the help from some kernel functions. On 32-bit is almost entirely in user land. So starting from the exception handling chain, let's say we start from FS segment register 0, and we have an exception registration record, and it points to the next record, and it has a handler function. I made a small visualization here. And then from that record, we have another record that is installed, and we have another handler function, and so on. So, and this is how you construct a simple handler chain. And we're going to see how we find the best match in such a chain. If you don't have any registered handler and a structured exception occurs, like an access violation, for example, the process would crash. So what can we do? How can we very simply register such a function? We can explicitly create an explicit exception registration record, attach our handler function, my exception handler, put it at the very start of the exception record list, and then we introduce an access violation there right through a null pointer. And then we just restore the original handler. So this is how we very simply, it's not very useful, but it shows the idea that I tried to explain earlier. In practice, we're never going to do something like that. But this is how you would hook up a very simple exception handler starting from the thread information block. And the signature for such a handler, we receive the exception record that matched this handler, the establisher frame, context record, which is the structure that we've seen at the very start, and the context information. And we're going to see each of these arguments has special meaning, and we're going to see what we can do with them. We can install a special translator. We can take a snapshot. We can walk the stack frame, each stack frame, and build a stack trace from this. And I have more details about using and symbolicating crash reports and using this very mechanism to build stack traces and rich contextual information to debug things that happened live, to debug them offline, as if they happened right there, basically to capture all the contextual information of a crash and debug it later on. So if we don't handle the exception, we just return exception continuous search to search for the next handler in the list that might accept this exceptional event. And if we have like a magic fix or a way to handle this situation, we might attempt to handle handle the exception and stop searching for another handler function and just continue execution. Basically, this would mean that, okay, I've done something to recover, and I want the instruction pointer to point to the next instruction after the one that faulted. So the execution is resumed from where it left off. Of course, we can do fancy things, like I said, in our handlers. Just a simple example, if we have an access violation from the exception record, we can extract the operation type. Let's say it was maybe a read or a write. And from the virtual address information, either if we have a virtual address or not, we can decide if it was read or write through a null pointer or not, or maybe it was a dangling pointer. And maybe we can log the information or try to recover if possible. There are situations where this mechanism is actually used for not for recovery, but for actually faulting things in. For example, when we might be doing some kind of memory mirroring scenarios where we on each access we try to cause such a fault like an access violation, And then maybe we do, let's imagine that we're trying to build something like address sanitizer. And for each access that we do on real virtual memory, we try to construct a mirror image of the memory that is accessed, and maybe do some bookkeeping, or maybe flag this memory, poison the memory to around a specific region to see when certain access patterns are violated, and maybe put up some logs or warnings that, let's say, an access within the poisoned region was happening. So there are legitimate scenarios for faulting in memory as it triggers this mechanism to leverage it to some other purpose, not just for logging or recovery. But there's too much boilerplate for such a simple handler, I must admit. So that's why there are special syntactical elements that we can put, like _ try and _ except. And the compiler, the MSVC compiler, will basically will try to build what we try to do by hand. We'll try to build behind the scenes. So we have here an exception filter, and we can get the exception information, and we can pretend it never happened if we're in the except block, and depending on what the exception filter actually returns, if it returns continue search or continue execution, we can decide what happens next if we execute the code in the except block, or if another match is searched, or if we let the application crash or anything. So get exception information, this highlighted function here, retrieves the computer-independent description of an exception and the information about the computer state that exists for the thread when the execution occurs. So all this context information, like the context structure and exception pointers. And this function can be called only from within the filter exception of an exception handler. So this function cannot be called out of context. For example, if an exception is not in flight, or if it's called from outside an except block. And the exception signature basically returns an exception pointer. I've put links to the documentation if people want to drill down more. The exception pointer structure is just another bundle that bundles an exception record that we've already seen and the context record that we've seen. That was the one with the CPU registers. So this is what the get exception information function returns. So going back to the exception filter would consume this new structure with the bundled information. So it receives the exception pointers, and based on what's in there, it can decide, for example, here, we decide that if it's not an access violation and if it's not a write fault, then just continue search and find me a new match, a new handler that will accept this event. If it is an access violation for a write fault, get the virtual address or where this write fault occurred, and maybe virtual protect the page, and basically resume execution from the faulting instruction. So now this page is writable. So the next time the instruction executes, it will succeed. So again, a very simplistic scenario here, but we can imagine more complicated things like a shadow memory, or placing special diagnostic flags, or setting up poisoned regions within the heap to detect some kind of weird scenarios, or maybe even imagine some kind of replay software that records memory access patterns, and it's able to replay all the allocations up to a given point, or maybe roll back allocations as they happen, like some kind of time traveling magic through the heap. So we can imagine all kinds of weird scenarios, and I've seen some. But why do we have to bother to understand all this? Because if nothing else, ignoring just the sheer joy of understanding how this works, we actually deal with C++ exceptions, and they are built on such machinery. So all C++ exceptions that are exposed through standard C++ underneath on Windows are implemented on top of SCH machinery. So the compiler does all the work. The C++ compiler does all the work and generates SCH code with special meaning, where special means the behavior that is expected from standard C++ exceptions. So C++ throw is mapped, for example, to raise exception in SCH, try catch, try and except with double underscores. Local variable destruction is handled through try and finally blocks, and CXX frame handler is mapped to roughly an except handler 3. This might sound like gibberish to you, but I'm gonna bet you that you've seen stack traces that where you've seen such symbols like except handler 3 or CXX frame handler. And you've probably wondered why they show up there, and why do I see these stack frames in my stack trace? And now you're going to probably understand why. And let's see a bird's eye view on how C++ exceptions actually are built up and maneuvered using SCH mechanism. So let's say we have a throw myException type, and we have a myException object. We have the CXX throw exception function that takes a void pointer parameter, of course, and a throw information. And in order to throw such an object as a C++ exception, we have to call CXX throw exception function, give it the pointer to the address of the object, this special object of type myException, and construct a throw information for this exception type specifically. And a throw info structure basically has lots of little pieces there. Some attributes, this information about the structure and the unwind information, and a catchable type array, again, information about what kind of types can be caught depending on what is specified within the program, that what types of exceptions can be caught by specific catch things that we mentioned in the program, and what exactly can be caught there, because the exception mechanism is eager and is trying to match more aggressively based on the type system and the hierarchy between the types that we use. And catchable type, again, has some properties. I'm not going to go into detail, some type information, of course. But by the way, all this works even without RTTI. So RTTI is not mandatory for this thing to work. And other bits and pieces about when exceptions can be copied, and of course, all the information about how the destroy happens for each object, the destructor functions. Of course, the compiler has to keep track of the liveliness of objects when each object is constructed within a specific stack frame, if an object was constructed or not, if it needs to be destructed, and the order in which these destructions need to occur during the unwind process. So lots of details, but I'm not going to go too much into those because there's no such time. And this function, very simplified view of this CXX throw exception function, might look like this. We have an exception record, again, like the toy example we've seen a few slides ago. The exception code is exception number, and this is a combination of MSC and a magic hex number there. The exception is marked non-continuable, and we have the following parameters: the magic number 1, the address of the object, the throw information that we constructed. This is all the richness, all the rich information about the type that is thrown and what kind of handlers are available within the module. And then we just call the API raise exception and pack all this information, and bam, this exception is in flight now. So we basically, all these messy bits basically helped us go from a simple object that any object type can be thrown in C++, from a simple object to all the information that the SCH mechanism needs to raise an exception, and all the information needed so that a handler can identify this exception, handle it if it chooses to match it, and all the unwind information that needs to happen if the scenario calls for an unwind situation. So all the structures that need to occur within the path, all the frames that need to be taken off the stack, and at each step, what functions need to be called, what destructors need to be called more explicitly. And of course, during all this process, other exceptions might occur. And then all hell breaks loose. So this is how a C++ exception is born. But what happens the other way around? Let's say we have a structured exception. So we have a low-level event, like an access violation, or maybe an overflow situation, or an arithmetic logical error, something like that. And we want to map it to a C++ exception. So the other way around, can we handle C structured exceptions as C++ type exceptions? And yes, the CRT gives us a way to hook into this mechanism through a function called setSC translator. And we can provide it with a special function that will be called, special function that we provide, that will be called when such an primitive exception occurs within the running thread. And we get a chance to, again, see what happens, get all the contextual information, and decide what to do next. And if we want to, map it into a C++, wrap it all into a C++ exception that we can throw again or handle in some other part of our application. Of course, each new thread needs to install its own translator function, because we've seen that it all starts from the thread information block. So we do need to call this translator function for each new thread where we want to install such a translator. If we want to automate this shim of injecting an SCH translator for each thread when it's created, we can easily create a shim wrapper for, let's say, for standard thread, and for each construction, basically shim our function. We see here our special namespace thread shimproc that forwards all the arguments that we received in this thread wrapper. And in this shim procedure that we introduce right before the thread starts executing, we call this function with helper function handle SCH, basically to handle structured exceptions. This is the function that installs the SC translator that I've shown earlier. So we can shim the execution or the creation of standard thread, and right before letting the thread run, we install this translator. So we can automate this process for each thread that we create, if we choose to do so. And this translation function receives, again, familiar arguments, the SE code, the code for the exception type, and again, our friendly exception pointers structure. And we can decide to handle or dispatch. There are a lot of exception types that just a few examples here fit on the slide. And we can decide maybe to log the particular exception that happened and decode the information, and maybe mine even more information. For example, we can do a stack walk. I have a whole other presentation on how to do stack walking, starting from such an exception pointer structure, and traverse the each stack frame and record information at each step, like symbol information and so on. Again, we've seen this before, same deal. Starting from the exception pointers, we can give special meaning to the fields within, depending on the exception type. Again, my favorite special case, access violation. Maybe it's because I see it most often. So we can decode and see what kinds of access violation we deal with, read, write, data execution prevention, and so on, and maybe log this information, construct something with it. We can trace, we can have a helper function to, let's say we have an utility that we've built like a stack walker and trace from context. And we start from the exception record within the exception pointers and just construct a stack trace in string form, let's say. And we can even extract symbol information very easily. There are APIs for that. Again, I have a whole other presentation on just this topic. I'm just going to mention it briefly here. It's very easy to use debug symbol APIs from the debug help library and extract symbol information from mapped from each instruction address. Of course, we have to do some take into consideration facts like SLR, base address randomization, to do the right arithmetic to figure out the right offsets of each instruction, to decode each function and map it to its corresponding symbol from the PDBs. And you can mine all this information, and lo and behold, you can construct a C++ exception that you can wrap everything within it, like the file that produces the line, exception type, and all the information that in which format we desire, like maybe a string representation of the stack frame of the stack trace here. So it's fairly easy to be creative and find ways in which to wrap all this information into a C++ exception, find all kinds of useful ways to handle it somewhere in the program. So this is about exceptions in flight, but we can get the stack trace for the raised exception on the current thread, right? So, for example, if an exception is not, so for example, get current exception context, we can call this API like we've seen the accept handlers and get exception pointers earlier on when we've seen bare metal SCH exceptions. Again, the corresponding thing that we've built here in C++ get current exception context can be called when an exception is in flight. Let's say we're in a catch handler or something like that. So again, we can use the same function that we've used for the SE translator, like trace from context. And instead of receiving an exception pointers structure in the callback that we register with the CRT, we can build a function ourselves that gives us the current exception context for the exception that is in flight, that P context that we need. And the same thing we've seen in the translator function. But in that situation, we received the P context, highlighted here in blue. That P context information was given to us by the CRT inside the exception pointers structure. So that was easy because we already got it, but we can obtain it ourselves in other situations. There's some magic things here. I'm not going to bother explaining the details because it's ugly, but there are ways to call some undocumented functions and do some magic maneuvering of addresses to get the pointer to the address of the P context for the exception in flight. And it's for older CRTs or older Visual Studio versions, if you still require that, there are ways to do it there too. I've put this, the whole code on slide actually works, nothing is omitted, but it's just ugly. And in order to get all these symbols and everything to work, you have to include some headers and even some private headers there. Don't bother about the details, that's not important now. It just works. And it works through this private structure that is defined in the VC runtime internal header. And it looks familiar. It kind of reminds us of the context structure that we've seen in SCH early on. And it has all the information that is required to build a contextual information about an exception in flight. And this is how the operating system through these protected private CRT APIs gives us access to the exception in flight without the need for us to decode everything starting from the thread information block. So we can think of this as P context a la carte. So we can get a hold to the in-flight exception whenever we want. But what if there's no exception in flight? Let's say we want to trace something or assert something or log something each time a particular function is called, and we want to see the whole call chain and maybe see when a particular function is reached, the whole call chain on how we got to that function and in what context and what was the way it was called, and maybe log something or maybe instrument something about that function without the use of attaching a debugger, because we can't always afford to attach a debugger when something like might happen live. So how can we get a hold of a P context then? So again, I've built here a very special trace from a very simple trace from caller function, and a way to do this again are some kernel functions. RTL capture context. RTL capture context basically gives us a way to obtain a P context structure from the given location. So from the point of execution when we invoke the capture context function here, here in red, the other part is just ceremony to dynamically load that function from kernel because there's no API signature for it. So from the point of calling this function, we can see the exact P context information of where we are now. And from that point, we again, with our helper function from the stack walker, we can trace from this context now and basically the same thing happens as if there was an exception at this p-context location or this p-context snapshot. So basically, either we have an exception and we get a snapshot from where it happened, or we on demand want to take a snapshot from the calling function at a particular location in our program. We can obtain this p-context information, and from there on, everything happens the same. So we can do a stack walk just the same. Traversing this information, we've seen this function called many times before. It's not very complicated. Trace from context. The main thing, the input information, is the context structure that we so badly wanted to obtain. And of course, we have to synchronize access to this because the debug help functions are single-threaded. So bad things will happen if we try to access this from multiple threads. And we can build symbol utilities to use the debug help library to extract symbol information and initialize a stack frame from context. We receive this context structure, and we can construct the current stack frame for this context structure, and then iterate each stack frame using the StackWalk API, and extract for each stack frame the address and the symbol information, and basically aggregate a chain of callable functions starting from the given context up to the module base address, or maybe a frame count limiter or something. Again, I'm not gonna drill too much on this because I've done so in a previous talk, but it basically boils down to extracting all the information from the context structure, basically the CPU register snapshot, and using that to archive everything that happened to be used later on if we choose to debug something offline from a snapshot that we've saved live in production, because this code can run in production, and archive all this information in case of when a crash occurs, and later on all this archived information can be debugged on the developer machine as if it happened live. So all these details and all this machinery, it's not just curiosity for curiosity's sake. It can actually be leveraged to extract all this information to be used later on. So again, these would be the APIs that help us find displacement information, and basically everything is tightly packaged up in this debug help DLL from the Windows SDK that we can use as a dynamic dependency for a project, and leverage all these APIs that I've shown here to extract this rich information. So more details about this process are in my talk that I've referenced already, the quest for a better crash. And if you're interested in such a topic, you can watch that presentation there. So one more thing, a way to handle the unhandled exceptions. So yes, there's a way to do that too. The SCH mechanism gives us a way to hook into unhandled exceptions. For example, no matching catch filter is specified, or something escapes, all escapes oral functions, even escapes main. We can install an unhandled exception filter, and there's an API for that, set unhandled exception filter. This is how the signature looks. And for example, we can decide for a particular exception code to basically call std terminate, and this is the default behavior. If we don't install an unhandled exception filter, basically the CRT did this for us. So the CRT before calling our main function, maybe not everyone knows, but our main function is not the main entry point for our module. There's a main function in the CRT that calls our main after doing this kind of setup. So if no handler is found and the exception leaves our main, the CRT will actually call std terminate to take down the process, and that's a good thing. But we can choose to install such an exception filter and maybe continue search and maybe log something or whatever, build some kind of mechanism around uncaught exceptions, or maybe rethrow them, and maybe some other parts of the application will handle them. There are scenarios where this makes sense, but it's very difficult to give convincing examples out of context. So the unhandled exception filter needs to be installed just once, and this replaces the existing top-level exception filters for all existing and future threads in the calling process. So you just have to install it once. It's not like the SC translator that needs to be installed for each thread. And again, the unhandled exception signature, our very friendly and familiar by now exception pointer structure. And from there on, can do basically the same things, translate from context and continue execution, present or record the error in some way, or just accept it and let the process terminate. So with that, I'm just going to mention that in the next C++ standard, in C++ 23, we're going to get a stack trace facility. And just briefly, it's going to have very similar current function. It's a static function and a way to get a basic stack trace back. So this is very similar from the thing that I constructed earlier, where we said get context from current exception. So again, we have 3 overloads here, but this static current function will give us the stack trace already constructed for the exception in flight. And there are ways to iterate through a basic stack trace, iterate its frames. And there are various convenience functions like toString to get the string serialization directly, and operators for IO streams, and it even works with range for loops and ways to extract description and source file information and so on. So basically everything that I've shown earlier, homegrown and with all the gory details behind the scenes, we're gonna get very nice wrappers for it in standard C++, and things that will work on hopefully all platforms nicely. And it will be very, very easy to get information about the exceptions that are in flight and construct stack traces either manually or automatically, because there's so many convenience overloads there that you can basically just toString it into existence, so to speak, starting from the exception in flight that we get with the static current function. So it literally can't get any simpler than that. So with that, if you have questions, we're right about at the time point to stop. But if you have follow-up questions or just want to chat about the scenarios I mentioned earlier, where all these nitty-gritty details come in handy, and actual scenarios that I can describe in more detail, where such facilities help applications in productions, and what we've built with such facilities in our application, and how we leverage the power of structured exceptions and all these mechanisms in the CRT. Feel free to chat about it with me, and I'll tell you a lot more. Okay, have a nice conference and see you around.